All right, guys, let's get started. Before we start, I just got the email from UH administration. Okay, so seeing we have will remain online teaching for 1 more week, so and we'll return to in-person class on Monday, January 31st. Okay, so this week and next week we still will be online, and then we'll go to campus on January 31st. Okay. All right, so 1 more week. So today we'll discuss chapter number 3, which is microstructure. So what is microstructure? In this class, it talk about the hydration product. Okay. Right. So we know in cement, we have 5 major compounds: C3S, C2S, C3A, C4AF, and also we have gypsum to react with C3A to slow down the chemical reaction of C3A. Okay. So we discussed this in early lecture, actually last time. And also this is a chemical reaction we call the hydration of cement for C3S, C2S, and C3A, which is more complicated. And also C4AF. Okay. And we know we have CSH, calcium hydroxide, action guide, or AFT, monosulfide aluminate. Okay, so as the major hydration product. So here shows the kinetics of hydration, okay, or the percentage of hydration for different compound. Okay, the x-axis is hours. It's timing hours. So what we can see here is for C3A and C4AF, they react pretty much instantaneously. Okay, and it goes up. For C3S, it will not hydrate until the first hour. Okay, but for C2S, it is up to, this is 10, in log scale, it's 20, 30, 30 to 40 hours, then the reaction, the hydration of C2S kicks in. And this is the, again, kinetics of hydration for hydration product. For AFT, action guide, so the formation is very fast and peaks after 30, around 40 to 50 hours. Okay. For CSH, okay, it slowly goes up beyond hundreds of hours. For calcium hydroxide, it will flat out after hundreds of hours also. So for AFM, it is very minor. Okay, so here shows the hydration formation as a percentage. As we can see from here, CSH will occupy the majority of the hydration product. Okay, then followed by AFT and the calcium hydroxide. It's about 20%. Okay. AFM is the minor products. So when we mix Portland cement with water, we know that the hydration goes up. Okay. So let's say this is the conceptual view of hydration. The black area is the Portland cement grain particle, okay, unhydrated. and water is the in between the cement particles. CSH as hydration product is in the stripped pattern. Okay. As we can see, initially we only have unhydrated cement and water. So during hydration, we have more hydration product, CSH, precipitate on the surface. So we have more hydration product, we have less water, and we have less unhydrated cement because these two phases are consumed. Right? So depending on the ratio of water to cement, so this is W over C. So W over C again is water to cement ratio. This is by far the most important parameter for concrete. So water to cement ratio controls almost everything, okay? Especially the strength of concrete. Okay. So if the water to cement ratio is larger than 0.32 after 100% hydration, which means the hydration stops due to lack of hydration, lack of water, or lack of unhydrated cement. So when the water cement ratio is larger than 0.32, all the cement is consumed. As you can see from here, there's no Portland cement grain. Okay, but there's some water left. Eventually, this water will evaporate, and the empty space, become a pores in concrete. And these pores will reduce the strength and also reduce the durability of concrete. When we have less than 2.32 water to cement ratio, then all the water will be consumed, but we have some cement left. Okay, but we have less pores, as we can see, that not much pores because we have enough hydration, unhydrated cement. Okay. So in another word, when the water cement ratio is low, we have less pores. The pore volume is lower. Also, we call that the porosity is lower for that concrete. Okay. So that will be beneficial to the strength and also beneficial to the durability of concrete. Here are some finals. Calcium hydroxide and AFT and AFN are not shown here, only show the major hydration product, which is CSH. And also here's the important notes here, note number 2. It says for complete hydration, 1 gram of Portland cement PC require about 0.32 to 36 gram of water. Okay, the density of Portland cement is around 3.15. Okay, so if we transfer 1 gram of PC into volume, you will find out 1 gram of Portland cement has almost the same volume as 0.32 gram of water. Okay, so we call that equal volume concept. The same volume of cement will fully hydrate with same volume of water. Okay. Then let's look at the morphology of different hydration products. Number 1 is CSH, calcium silicate hydrate. The size of CSH is very small, so 1 times 0.1 micrometer. It is very poorly crystalline structure, or we call that reticular network. That's not well-defined crystal structure for CSH. Okay. CSH take more than 50% of the total solid hydration product. It is hydration product provide the strength and also the durability of concrete. Okay, so by far the most important hydration product is CSH. We also know the ratio of calcium and silica is not fixed. Okay, it's between 1.5 to 2 in most of the case. So CSH looks like a topomorite, which is the picture on the lower right. So topomorite is a natural mineral. Okay, structurally, CSH from hydration of cement is pretty much similar to CSH. Pretty much similar to topomorite, sorry. Okay, so question from Jonathan said, what is the lactate? Lactate. Okay, so all water reactive cement lactate is some remaining cement here. Okay, so cement is not fully consumed. So we say cement, some cement is left. Okay. So the water lactate, means the water is some water is remain after all the cement hydrated, but this water will eventually evaporate to the air, to the outside of concrete. Okay. But unhydrated cement, they will stay in the concrete all the time. All right, so this picture shows the nanostructure of CSH. Okay. So the black lines is actually CSH sheets, the layered structures. Between the sheets of CSH layers, we have waters. So the green cross are water. Okay. And also we have some other water in between the CSH sheets and also in the pores, the empty space, the glaze. Okay. So CSH is layered structure. So this is a scanning electron microscope picture, shows CSH in different structure types. Okay. All right, so let's talk about the three major types of CSH, depending on the morphology and location of them. Okay, so the first one is called shrinking core type. Okay, so this, the white color, this is unhydrated cement. As we can see from here, this is one unhydrated cement grain. And on the surface of this unhydrated cement, this is CSH. Remember the three words: dissolve, diffuse, and precipitate. So CSH precipitate on the surface of CSH unhydrated cement. Okay. And the core of the unhydrated cement is shrinking. So we call the first type shrinking core type. For the shrinking core type, so CSH surround partially hydrated cement grain. Okay. So that is caused by transformation of C2S and C3S directly into CSH in situ. Okay. And remember, we also have calcium hydroxide due to the hydration of C2S and C3S. And this calcium hydroxide will pass into solution and deposit in other places. Okay, and we call the first type shrinking core. The second type is called Hedwig green type. Okay. At the same time, same area, some of the green shows heavily green, and the others shows the shrinking core type. Okay, so the heavily green actually is a thin skin precipitation of CSH on the surface of unhydrated cement particles, and then sometimes it will hollow out. Okay, as we can see from in this picture. Okay, look at here. The brightest color again is unhydrated cement, and this layer is CSH, the heavily green. Okay, we can also see space. The space in scanning electron microscope shows as black color. If you see the black color here, here, or here, that means they are empty space. They are voids. Okay, so we can see that's the voids between unhydrated cement and the CSH, and we call that heavily green type. Okay. So it forms a thin skin and hollow out from within it. Okay, due to dissolution. The size occurs mostly in smaller clinker size, okay, 50 micrometer or less. Okay, that's another name for heavily green. It's called hollow shell hydration green. Okay, because we have a hollow space between the CSH and unhydrated cement. The third type is called outer product or ground mass. Okay. So this type of CSH, they dissolve from clinker and they precipitate between the cement green particles. Okay. Together with calcium hydroxide. And this will form a very porous ground mass. And of course, the porosity will reduce when we have more hydration product. So the ground mass is the areas between cement particles and between the aggregate. Okay, so the ground mass include CSH, calcium hydroxide, ethylene guide, monosulfide aluminate. Sometimes also flash if we have a blended component in concrete, and also air voids. As we can see from here, right? This particle is unhydrated cement, and we can see we have a precipitated CSH on the surface. So that is a shrinking core type. In between the cement particles, the areas, we have a mixture of CSH, calcium hydroxide, and other phases. Okay, and we call that ground mass. The round particle here is flash particles. We'll talk about flash in future lectures. Okay. So the CSH in the ground mass is very different in morphology. In other words, the shape of CSH in the ground mass is different from the CSH in the shrinking core. Okay, but chemically, they are pretty much the same. So we talk about three types: the ground mass, the shrinking core, and also the heavily green. So chemically, these three types of CSH is very same, but they occur in different places. So look at the CSH, look at the scanning electron microscope picture. the brightest color will be unhydrated cement. Okay, the black color is empty space, like here and here. CSH is in gray color, and in a moment we'll talk about calcium hydroxide. Okay. Calcium hydroxide is very well defined hexagonal crystal plate, as you can see from here. So we have hexagonal crystal plates. The size of calcium hydroxide is much larger. It's in millimeter level. Take about 20% of the total solid volume. So calcium hydroxide has lower strength compared to CSH, and it is also soluble in water. Okay. As a result, it has adverse effect on strength and durability. So calcium hydroxide, as we can see from here, is also very bright. It is actually the second brightest phase in SEM picture of cement, hydrated cement. Okay. Again, the brightest color is unhydrated cement. The second brightest color is calcium hydroxide. Okay. The gray color CSH, the black color are voids. Okay. AFT and monosoft aluminate has similar gray scale compared to CSH. Okay. So let's look at calcium hydroxide. So they are much larger compared with CSH, a few tens of micrometer in length, sometimes in millimeter level. Okay. Outside, it is very irregular. They may have some holes in calcium hydroxide. Calcium hydroxide deposit in empty space, actually. Okay, because calcium hydroxide formed by combining calcium ions and hydroxide ions. Okay, whenever there's an empty space in the system, calcium hydroxide tend to fit in that space. So that's why we see calcium hydroxide deposit mostly in fitted out space between early deposits. Now look at here. So much of the periphery, so the outside surface around the sand and of course algae green is covered with layer of calcium hydroxide. If you take 375 before, you know the boundary between algate and cement paste, we call that ITZ, or interfacial transition zone. Okay, so in the ITZ area, or the boundary of algate and cement paste, very often we can find a lot of calcium hydroxide, because again, calcium hydroxide tend to deposit in some out space. So whenever there's a space, such as the ITZ, calcium hydroxide tend to occurs there. Okay. As we can see from here, this is the calcium hydroxide around algate. So this big areas on the upper left is a sand particles. Okay. The scale is 40 micrometer. Calcium hydroxide in the boundary or the ITZ between the sand and cement paste. Okay, so that is calcium hydroxide. And this is unhydrated cement. And in between, one mass. We can also see from here, there's a crack. You know, again, empty space is black color. Okay, so there's a crack here. And here shows calcium hydroxide within cement paste. Okay, so calcium hydroxide can occur not only on ITZ, but also in the grand mass within the cement paste, such as here and here. It can even be found within airways. So this round, big black area is air bubble. Okay, so we put air in concrete either on purpose or by accident. Okay, such as we do air entraining agent to increase the concrete's resistance to freeze and thaw. Okay, in this case, in this picture, we see calcium hydroxide deposit within the airways, like here, and also around the airways. Okay, again, whenever we have some empty space, then calcium hydroxide tend to deposit there.
If that is an air bubble, why isn't it black like in the other images?
Why is black?
Not black.
This is black. This is black, but we have some calcium hydroxide within it.
That makes sense.
But most of it is black.
Okay, okay.
Yeah.
So there's particles that are unhydrated cement that got cut in the bubbles. So that's why it has like that sparkle.
It is.
Thank you.
Yeah, it is. Yeah.
That makes sense. Thank you.
Okay. In the future lectures, we also discuss SEM, scanning electron microscope, and how and why this machine works, and how this machine just send electrons into the samples, and depending on the reflection, because in the air bubble there's nothing, okay, and nothing can reflect the electron, and that's why we see black. Okay, if reflection is higher, in the case of unhydrated cement, we see a much brighter face. Okay. All right. Then let's look at the third phase, which is etching guide or AFT. We also call that calcium sulfur aluminates. It is a needle-like materials. Okay, hexagonal plate, crystal, but with very large aspect ratio. So it's very long, but the cross section, if you cut the cross section, is hexagonal plate. Okay, so that's a needle-like shape. The size 10 times 0.5 micrometer. Together with monosulfide aluminate, etching guide take about 15 to 20% of total solid hydrates. It has a minor role in structural behavior, does not contribute to the strength at all, and it potentially will cause durability issues such as software attack, as we discussed before. Okay, so etching guide is not good for concrete, but we cannot get rid of etching guide and the monosulfide aluminate in our Portland cement, so we have to deal with that. It does not contribute to the performance of concrete. Monosulfide aluminate, the size 1 times 1 times 0.1 micrometer. Again, has minor role in structural behavior. It is a thin hexagonal plate crystals, as you can see from here, compared with the needle-like etching guide. The last phase is unhydrated clinker grain or unhydrated cement, depending on the water to cement ratio. Okay, if the water cement ratio is less than 0.32, in theory, we have to have some unhydrated clinker grain left, remain there. Okay, or if the cement particle is too big, a rule of thumb is if the diameter of the cement particle is larger than 60 micrometer, 60 micrometer, then the core of the cement grain cannot be fully hydrated. the water cannot fully penetrate and 100% hydrate the cement grain because the particle is just too big. So larger than 60 micrometer, it cannot be fully hydrated, no matter the water cement ratio. So remember that. Unhydrated cement clinker is pretty strong. It's similar to the strength of CSH. So if we have some unhydrated cement clinker in the system, it is actually a good thing. Okay, so that's the reason why when we reduce the water cement ratio, the strength of concrete is higher typically.
I have a question about the clinker grain. So you mentioned that eventually water will evaporate. You know, if there's a lot of water, it will evaporate out of the concrete.
Yes.
Can it go the other way around? That is, eventually water can penetrate in and eventually hydrate those grains, or no?
You know, if the concrete dries out totally, actually, if the relative humidity inside the concrete is below 80%, the hydration, the chemical reaction will stop. Even though you wet the concrete again, you will not, restart the hydration process. So the concrete dries out, everything will stop. There may be some minor reaction goes on, but it's nothing major there.
Okay, thank you.
Yeah. And this table is coming from our textbook, showing us the specific gravity of the major hydration product, the morphology, the size, and how we can see them. Okay, for example, CSH, its specific gravity is 2.3 to 2.6, which means the density of CSH is about 2.3 times the density of water. Okay, so very poor crystallizability compared to calcium hydroxide, very good crystal structure. The size and also how we can see them. For CSH, we can see using scanning electron microscope, SEM. TEM is for transmission electron microscope, and OM is for optical microscope. Okay, so these are the major hydration products. Let's look at the water, different type of water in hydrated cement paste. Okay. There are at least 4 different major type of water in the system. So the first one is called interlayer water. That's the green cross between the CSH sheets. Okay. So again, the black line is CSH sheets. Okay, or we call that CSH gel. The water between the layers is very hard to lose. Only lose when the RH or the relative humidity dry below 11%. Okay, so that's the first type of water. The second water is called capillary water. So that's the water in the pores of concrete. We have different type of pores, which we'll be discussing in a moment. But the water in the pores can be called free water if the pores is larger than 50 nanometer. The water in smaller pores, when the water evaporates, it will cause the concrete to shrink. Okay. Sometimes the concrete will crack due to too much shrinkage. Because when water leaves smaller pores, we have so-called capillary retention occurs. Okay. So we have a dedicated lecture talking about shrinkage mechanism of concrete. Okay. We also have adsorbed water. So that's the water on the surface of solid up to 6 layers of water molecule, which is the blue circles here. And finally, we have chemically combined water, which is the H in CSH. Okay, so this chemically combined water is very hard to lose. Can only last when we burn the concrete to very, very high temperature. Okay. So normal heating and drying, this water will not lose. And then let's talk about the voids in concrete. Okay. The smallest void is called interlayer space in CSH. It is in nanometer level. We also call that gel voids. So gel voids does not impact the strength and durability of concrete. So that is an intrinsic property of CSH. The capillary voids is in micrometer level. We also call that porosity. Depending on the water to cement ratio. When we increase the water to cement ratio, we have more this type of voids, the capillary pores. The more capillary voids, the concrete will be weaker. Also, the permeability will be higher. As a result, the concrete will have lower durability. So more capillary pores, the concrete will be weaker and less durable. The third type is called air voids, which is even bigger in millimeter level. Okay. So we have two categories within the air voids. The one is called entrained air. Entrained air is putting the concrete on purpose by using air entraining agent. In the case of freeze and salt, when we put entrained air, these tiny air bubbles will increase concrete resistance to freeze and thawing. Okay, in winter condition, we may want to put air entraining agent in concrete. So that's the first type within the air voids. We also have entrapped air, which is much larger. Okay. So entrapped air is the voids we do not want in concrete. It is due to the concrete is not fully compacted. Okay, so we're trying to eliminate entrapped air as much as possible. Okay. So the pores in concrete is very, very important because it will affect both the strength and also the durability of concrete. Okay, so at the beginning, the voids may be saturated because we have enough water in it. Okay, we call the water in the concrete pore solution because it is not pure water. We have some ions such as calcium hydroxide ions in that, so we call that pore solution. So the original concrete pores is saturated, sometimes partially full or empty. But eventually they will be empty, dries out, unless the concrete is repeatedly wet and dry. Okay. So here shows a picture of air voids. And here shows the voids within the heavy green. This is the second type of CSH. And also here, and also here, also here. And here shows the residual heavy green voids in dense paste. Okay, so here we have air voids around the bright color. Again, this is unhydrated cement. We also have voids here and here, and also here. So as we can see in a normal concrete paste, a lot of voids are pores inside it. Okay, the less voids, the better. Okay. All right, so far we have talked about so many different type of hydration products, different type of voids, and here summarize the size of them. So from interparticle space between CSH sheets, which is in nanometer level, capillary voids is in nanometer, tens of nanometer or micrometer level. Okay. Calcium hydroxide, tens of micrometer. Entrained air, hundreds of micrometer, to entrapped air, which is in millimeter level. Okay, so the range of size for different phases is very big. All right. So this table, again, from our textbook, summarize the different type of voids or pores depending on the size. Okay, so you may ask why we care so much about the size of the pores. Okay, anyway, they are empty space, but they will affect performance, especially shrinkage of concrete significantly. So the water in different type of voids, depending on the size, when the water evaporates, they have a totally different behavior on concrete. And we know concrete is very brittle materials. Too much shrinkage, the concrete will crack. That's the reason we care about the different type of voids. So let's look at here. If the size is between 50 nanometer, larger than 50 nanometer, okay, we call that large capillaries or macropores. Okay, the water in the macropores, we call that free water. The water leave and get in does not affect shrinkage of concrete too much. The second type of pores is between 10 to 50 nanometer. Okay, we call that medium capillary pores or large mesopores. Okay, below 10 micrometer to 2.5 nanometer, nanometer, 2.5 to 10 nanometer. So we call that small isolated capillaries or small mesopores. And between 0.5 to 2.5 nanometer, it is called micropores. And below 0.5 nanometer, it is the interlayer space between CSH sheets. Okay, so we have 1, 2, 3, 4, and 5 type of pores depending on the size. And let's look at, different categories, the role of the water in it, and how, what kind of property of concrete it may affect. Okay. The micropores, which is larger than 50 nanometer, the water in it is called free water, or we call it bulk water. These pores will affect permeability and diffusivity of concrete, and that's about it. Okay, not too much on shrinkage behavior. For large mesopores, which is between 10 to 50 nanometer, okay, here, a second. When water leaves from this pores, it will cause a small amount of surface tension. Okay, surface tension is the force make concrete to shrink. Okay, the harder surface tension, the more shrinkage concrete will experience. It will also affect the permeability of concrete. Okay, so the water in the large mesopores account for shrinkage above 80% RH, 80% relative humidity in the concrete. For smaller mesopores, which is between 2.5 to 10 nanometer here. So the water leaving this pores will cause large surface tension, cause large shrinkage. So that occurs between 50 to 80% RH. Okay. And for micropores, from 0.5 to 2.5 nanometer. Okay. So that's the adsorptive water. The shrinkage may occur at all different levels of RH. We also cause concrete to creep. Okay. But the water in this micropores, there's no surface tension. So no menisci formed in such a small pores. Okay, so again, we'll talk about shrinkage behavior and creep of concrete in lecture 10 or 11. Okay, several weeks from now. Let's look at hydration again. So here shows a virtual experiment. Let's say we have 100 cubic centimeter of cement, and the water to cement ratio is 0.63 by weight. Okay. So based on this information and also the density of cement, the density of cement is around 3.1415. Density of water is 1 gram per cc. Okay, so we can calculate the volume of water, which is about 200 cc. Okay, so initially we have 100 cc of unhydrated cement, the blue color, and the white color is 200 cc of water. Okay, so let's see, for D7 we have 50% of hydration, which means 50% of cement is consumed, hydrated. Okay, so we have less cement, we have more green. The green is hydration product, and we have less pores. This volume is occupied by water. Remember, the water will eventually evaporate. I will say, unconsumed water will eventually evaporate. Okay. At day 28, we have 75% of hydration. And after 1 year, we have 100% of hydration. Okay. At that time, we have no unhydrated cement. Why? Because the water cement ratio is larger than 0.32, or cement is fully hydrated. So we just assume that. Okay. And we have a lot of hydration product, and we have some capillary pores. Okay. But remember, the total volume of cement paste is always around 300 cc. Okay. So after the initial set time, which is 2 to 4 hours, the total external volume of cement paste will not change almost at all. Okay, so the total external volume, as we can see from the notes here, will not have big change after 2 to 4 hours. So the picture shows here just show the total volume of the pores. Okay, so after 100% hydration, we have this much of hydration product, around 200 cc, and we have around 100 cc of pores. If we reduce the water to cement ratio, then the capillary pores, the volume of that will be lower. So here is another experiment. It shows us the effect of water to cement ratio. Okay. Again, we consider 100 cc of cement, but all the cement will 100% hydration. Let's say after 1 year. So all the cement is consumed if the water to cement ratio is larger than 0.32. As you can see from here, so we have 5 samples. The water cement ratio is 0.7, 0.6, 0.5, 0.4, and 0.32. Okay. So when the water cement ratio is 0.32, we have fully hydration. All the cement is consumed, all the water is consumed, there's no capillary pores left. So that's very good because the more capillary pores, the concrete will be weaker, and also concrete will be more permeable. So in series, concrete will be less durable. So we can see here, the higher the water cement ratio, we have more capillary pores. In other words, lower water cement ratio, we have less porosity, we have higher strength, as we can see from this curve. Okay. So if you read your textbook, I just show you the page 81 to 84. If you don't have the textbook now, you don't have to, but just let you know, we have an equation to calculate the volume of the pores depending on the water cement ratio, degree of hydration, and so on. Okay. And this table, also from the textbook, shows us the physical information, including specific gravity of hydration, the compound, and also the hydration product, including the specific gravity. Okay, so focus on this. So we just discussed the lower the porosity, the higher the strength, and the lower the permeability. Okay, let's look at here. So the picture on the left shows the solid to space ratio. So the solid to space ratio is 1 minus P. P is for porosity. Okay, basically, porosity is defined as the void to total space ratio. So 1 minus P is the solid to space ratio. The red line is the permeability coefficient. Okay. The blue line is the strength. So the XL on the top, it shows the porosity. So what we can see is here is when we increase the porosity, the strength goes down, the permeability goes up. For normal concrete, the capillary porosity is around 0.3 to 0.45, as in this shaded area. So very clear. The lower the water to cement ratio, we have higher strength and lower permeability. Okay. What is here? Here shows the capillary porosity. The y-axis shows the water to cement ratio, and different lines shows different degree of hydration. So what we can see from here is, if we increase the porosity, we increase the water to cement ratio, then the porosity will also be higher. But for the same water to cement ratio, such as 0.5, for example, the higher degree of hydration, we have a lower porosity. Okay. So we know porosity is very important for performance, including the strength and also permeability. And permeability is the most important parameter controlling durability of concrete. Okay. So porosity obviously is very, very important. Here shows how we can measure porosity. Okay. We can measure the electrical resistance. We can use image analysis using NMR, which is the nuclear magnetic resonance, which is not used very often. We can use the weight loss method or mercury intrusion porosimetry. Okay, so these are one of the methods we will discuss in future lectures, or we can use computer simulation. Okay. So let's just quickly go over different type of method. The first one is based on weight loss, okay, or TGA, also called thermal gravimetric analysis. Okay. So for this type of method, we put the sample in the oven, and we gradually increase the temperature of the sample. Okay, so at certain temperature, certain phase will decompose. For example, calcium hydroxide will decompose at 800 degrees Celsius, for example, and CSH decompose at another higher temperature. So we monitor the temperature versus the weight loss of the sample. So based on this method, we can estimate the weight of different phases inside the sample. Okay, so the concept of TGA method is very simple. Again, we'll discuss this in more details. MIP will also be discussed in future lectures. Okay. For this method, we push mercury inside the pores of the sample. Okay. We monitor how much mercury can be pushed into the sample versus the pressure. Okay. The pressure could be very high, up to 200 megapascal. So the higher pressure, the mercury can be put into smaller pores. Okay. So based on the correlation of the pore size and also how much mercury can be pushed into the sample, we can have something like this. This is the pore size of the sample, and this is the penetration volume of the mercury. Okay, so we can use MIP to get the pore size distribution, the porosity, the surface areas, and other information of the sample. Okay, we can also use image analysis. This is the clinker picture. Depending on the morphology, we all know from previous lecture, the angular light color is C3S, the round shape, dark color is C2S, and in between these particles are, we call that liquid phase, which is a mixture of C3A and C4AF. Okay. And also this is a picture of hydrated cement paste. We can see ethylene guy, we can see hydrated clinker. Okay, this is the 0.45 water to cement ratio. Okay, as 7 day, the scale is 30 micrometer. The black color is empty space. Okay, based on the picture, because empty space is in black color, so we can just count out what is the areas of the voids and estimate the porosity from there. This is water to cement ratio 1 day. As you can see, much more black area, much more porosity compared with 7 day. All right, so here some discussion about the interfacial transition zone. Again, the interfacial transition zone is the boundary between the aggregate, such as sand and coarse aggregate, and also the cement paste. Okay, so the thickness of RTZ is around 30 micrometer in series. Okay, supposedly RTZ is weaker because it's supposed to have more pores in that 30 micrometer zones. Okay, but maybe not always be the case. Okay, here shows 100 days total concrete. The areas on the upper right is the aggregate. Okay, the RTZ will be these areas between the aggregate and the cement paste, the ground mass. Okay. From here, we may see more black color or voids on ITZ, but not very significant, not like a clear cut, weak, porous ITZ here in this picture. Here shows early age. This is a 3-day-old concrete. This is ITZ. Again, this is aggregate. This is ground mass. We can see clearly more black color or pores in the ITZ area. Okay. Because this is early age, only 3 days old. We have not enough hydration product. When the hydration process goes on, we will see more and more hydration product, especially calcium hydroxide, precipitate and fill in these voids in ITZ. So here shows another picture, the ITZ. We can see one is calcium hydroxide. Again, the second brightest color in this picture is calcium hydroxide. The most brightest color, the brightest color phase is unhydrated cement. So we can see clearly on ITZ we have a lot of calcium hydroxide because, again, calcium hydroxide tend to deposit into empty space. As long as there's a void there, calcium hydroxide tend to find that void and fill that void. Okay, and also we have areas of defect bonds between these sand particles and the ground mass. Okay. So sometimes we cannot find a clear-cut ITZ, like in 100 days old concrete. Okay. So why there's no clear-cut ITZ? Okay. So initially we have a porous zone in the ITZ areas due to the so-called preferential exclusion of larger clinker particles from the aggregate surface. So we also call that the wall effect. So compared to the size of cement clinker, the sand and the coarse aggregate is much larger. It's like a wall to the cement particles. Due to particle packing series around the wall of the cement, aggregate surface, we have less larger clinker particles near the wall. So that will cause an intrinsic higher porosity on the wall surface, on the surface of aggregate. Okay. However, as we discussed, hydration occurs when we have calcium hydroxide, and calcium hydroxide tend to fill this empty space, the ITZ. Okay. Ground mass, such as CSH, can also help to fill this residual space. Okay. So that will, reduce the difference in porosity between the ITZ and the remaining area. Okay. So here is some of the research. Study this is the percentage of CSH, which is the wax cell, versus the distance from aggregate. So we know traditionally between 0 to 30 micrometer, that's the conventional ITZ area. We study at 3 days and 100 days. So what we can see here is at 3 days, the areas of CSH, not too much difference from remaining areas. At 100 days, again, not significant difference between that. Okay, so I think many factors may explain that, including water to cement ratio. In some scanning electron microscope picture, we see more porosity, higher porosity in ITZ sometimes we cannot see that. Okay, so not always a clear-cut ITG. Here we talk about some models, okay, which can also help us estimate the porosity and study the hydration process. Okay, this is one model from NIST or NIST. So NIST is for National Institute of Standard and Testing. That's the government agency in Washington, D.C. Another model we're going to discuss is from Delft University in Netherlands. Okay, so we have some other models nowadays, but here are some of the early famous models study the hydration of cement. Okay. So this is the Delft model. Okay, the gray color is the unhydrated cement. So the yellow is water. The red color is the hydration product. Okay, so as you can see over the time, you see more red color, the hydration product precipitate on the surface of cement clinker and also around areas. Alpha is the degree of hydration. So we have a higher and higher alpha. Okay. This is the NIST model.
Before the hydration simulation, particles of cement are arranged on the computer display. The computer determines regions of the particles that can dissolve into water. The bits of dissolved cement diffuse through the water in a random manner and react to form solid phases according to certain rules. After a cycle of dissolution, diffusion, and precipitation is complete, the computer proceeds with another cycle. As this process repeats again and again, the microstructure develops, building bridges between particles that provide strength to the material. Computer simulation has proved valuable because it allows researchers to test conditions and make measurements that are difficult to achieve in real life. At the end of the hydration simulation, the structure of the hardened cement paste is very similar to that observed under the microscope.
Okay, so that's the NIST model, the NIST model. All right, so in lecture 3, we discussed different type of hydration product. The most important one is CSH. We also discussed different type of water and different type of voids together with the solid, the hydration product. We also see how the water cement ratio, the alpha, degree of hydration, will affect the strength and also porosity. Okay, so this is the introduction of the hydration and hydration product for cement chemistry. And yeah, that's about it for lecture number 3. Any questions? Any questions?
Yes. You know, in the previous slide that you did, which is slide 50, you talked about the computer modeling system. Oh yeah, all of this stuff. So like, how do researchers gather the data to create these samples? I'm trying to like think it in the realm of like what's his name? Like for deep learning purposes, or for like other modeling. Like, how does one gather the data to construct these types of models?
For this is based on experimental result.
Right.
For example, they can measure, for certain degree of hydration, what's the volume of hydration product can be generated, and they all have it's well established equations to estimate. I think this models is based on that experimental result. What exact programming tools, I'm not sure, but all the tools is based on the experimental results. such as this.
Right.
These models are very old, maybe like 20 years old. I'm pretty
Right.
sure that's the newer models based on, right now it's artificial intelligence, deep learning method. I'm sure that's a papers and the models working on these research areas. If you are interested, you can do some literature research and write a paper on that. Remember,
Yeah,
term paper at end of the semester.
Yeah, because the only thing I could think of like to gather data was to just take one of the testing types like mercury or even the photo based research, and then just compile like multiple images that would then have the computer measure the range of like where the pores would be, or even the ITC zone. Like that's how I would think that they would have generated the data, but I'm not quite sure.
Maybe like a finite element method or discrete element method.
Right.
For this type of model, they just generate a virtual space and they put the particles, there, and then like you see from the depth model, the hydration product just grew from there based on whatever method you use. Yeah, I'm not a simulation person.
Okay.
I'm more prone to experimental testing, cement chemistry, but I do a little bit of modeling, but not on hydration. Yeah, I did some modeling on packing density of aggregate and sand, but this is not my field of expertise for sure. Yeah.
Okay. I was just thinking how they would gather data, because it seems like it's a new area of research.
Yeah. One of my PhD students, she's working on use deep learning to help us better design different type of concrete. We see some promising result.
Oh. Okay.
Yeah. So yeah.
Very interesting.
Okay. Yeah. Thank you, Joshua. Any other questions or comments? Okay. All right. Thank you, guys. Yeah, sure.
Oh, sorry.
Okay. Yes.
Well, I had a question about testing and the sequence of testing. So many tests are safety tests to make sure, you can't use this concrete if it exceeds this limit or something like that, right? But how does that happen in the field? Because of course you can't do the test until you've poured, water in, and then, you won't know the answer of the test for 7 days or something. And by then you've already poured the concrete. So my question is about the sequence for testing.
Yeah, so before they go to the field, they must do a series of laboratory tests to ensure the fresh property, including the slump, the strength for sure, and other performance. Everything looks all right in the lab, and then they do that in the field. They also have a field test, so slump, air content test, for example, and then they take samples and bring the samples back to the lab to do 7-day and 28-day stress. So yeah, they pretty much ensure everything in the lab before they actually cast the concrete. And in the field, they also do the quality control tests, like the slump and air content test.
So they would take like a small amount of the dry concrete and hydrate it and perform a test on that. And then the rest is still sitting there waiting to begin the hydration and all that.
Yes. Yeah.
Okay.
Yeah. Okay. All right.
Okay, thank you.
Yeah. Thank you, David. All right, guys. Any other questions in general? Okay. I will see you on Thursday this week. Thank you.
Thank you.
Okay. Bye.
Bye-bye.
Bye.